So everything that we've done up to this point has had a common theme. It's a univariate analysis, meaning that we are predicting one outcome at a time from one person, and we're assuming that people are independent. So even though we're using generalized models that change our assumptions about the distribution from something that's conditional normal to conditional something else, and we're using link functions to make sure that the predicted outcomes stay within the boundaries of their possible values, all of this is predicated on the idea that we have a cross-sectional independent sample. So this would not work for kids that are nested in classes or schools. This would not work for longitudinal data. This would not work for dyadic data, for instance. So anything where you have a sampling unit that is measured repeatedly, this is not appropriate for. But the good news is that we can take all of these same tricks and add to them in order to make it appropriate for data in which you have more than one observation per sampling unit. So you're going to hear me start to change my terminology, and I try to watch this, but it's instinctive. You will hear me say model for the means sometimes to refer to the linear predictor and the fixed effects. Up to this point, whenever we're talking about variance, it was related to conditional distribution. But now we're adding a different feature. How should the residuals from the same sampling unit get to be related? That's the extra concern that we have to address when we have more than one outcome per sampling unit. And this is the idea of the model for the variance. So we've tackled what kind of distribution we need up to this point. Now it's how do we build residual correlation into that distribution as an additional concern. So multivariate models then are used whenever you have dependent data. Pause for reloading my caffeine here. Or as I recently saw on a manuscript that I was associate editor for, a title where they said non-independent. I'm like, I believe we have a word for that. It's dependent, not independent. So dependent data is a term that statisticians use to describe residuals being associated because they come from the same sampling unit. The extent to which you have dependent data is an empirical question. You can look to see whether or not the residuals from the same sampling unit are correlated and then decide what to do about it. So situations in which this would apply, repeated measures data. So repeated measures could take on multiple types of forms. It could be a longitudinal study where you're measuring the same outcome repeatedly over time. It could be an experiment where you have people, say, perform, they have to take a test while listening to classical music, and then they have to take the same test while listening to Metallica, and then they have to take the same test in silence, something like that, where the conditions are happening repeatedly to the same person within subject's manipulation. Dyadic data or family data is another case of this, where I have, say, like a caregiver and a patient, or perhaps people in romantic dyads, or perhaps a parent and a child. And if you want to be able to say, like, my parent's predictor affects my child's outcome, and my child's predictor affects my parent outcome, and vice versa, all of that stuff at the same time, we have to address the fact that people come in pairs, and their outcomes are going to be more related than people from different pairs. People from the same group. So technically, clustered data is dependent data if you think about it from the perspective of, let's say that we have kids nested in schools. What you have done is measure a school multivariately by getting scores from multiple students. So you can think about like student A and student B as like repeated measures on the school. It's the same concept, just at a different level of analysis. So this concern is relevant whenever you have a unit that has been sampled repeatedly, over time, over conditions, over people. One key distinction, though, in describing types of multivariate dependency and thus what kinds of options you have is whether it can be characterized as balanced or unbalanced. These words are used differently from different people, so let me tell you what I mean by this. A balanced structure is when everybody has the same potential set of outcomes, but not necessarily complete data. So like if I have performance in condition A, B, and C, and those are the only choices, and everybody gets like the same version of what I'm calling A and B and C, that's balanced. Even if somebody skipped session C and they only have data for A and B, still balanced because there's only 3 like finite possibilities. If I go into a school and I measure every student like at the first week of classes, they all get measured the same day. And then I come back, 2 months later and I do it again. And I come back 2 months later and I do it again. It's all the same day. That's balanced. Whereas if I had something like a rolling, I can only see 10 kids at a time. So I come in 1 week and I grab 10 kids, and I come in the next week and I grab 10 more, and I come in the next week and I grab 10 more. Until it's time to start the whole thing over again, then like time 1 is not the same time 1. So that would be unbalanced. Like there's an infinite number of possible levels of my conditions that are being repeatedly measured. What we're dealing with in this class is balanced. Unbalanced is my other classes. So if you have unbalanced, you need training in multi-level models. There's really like no other way to go about it. I have separate classes for clustered multi-level models and for longitudinal multi-level models, and those classes will come back every 2 years or so. Another example of this would be item data. So I know a lot of you are in psychometrics. If everybody responds to the exact same set of items, that's balanced. Whereas like if you are making, say, generating items on the fly, like automatic item generation from like a set of features or something to where there's like an infinite set of possible items, I'd call that unbalanced. So we're dealing with the balance case in this class. So questions or comments on that distinction, because it's a big one. Doesn't mean it's complete. Just means that the same possibilities hold for every sampling unit. All right, so there are a couple different ways that you can approach these models. One is by tricking univariate software into doing multivariate analyses. So that's the first thing that I'm going to show you. I have a couple examples of that from previous classes that I directed you to on the website. I'm deciding not to spend a whole lot of time on this semester. So the packages that would be relevant in this situation is mixed. So that is what it is called in SAS, Stata, and SPSS. Mixed, it stands for mixed effects models. In R, the function that we're going to be using is GLS, stands for generalized least squares within the NLME package. If you have a situation in which every variable in your analysis is either a predictor or an outcome, but never both at the same time, you can do this. So situations in which you might want to go this way, a traditional repeated measures ANOVA. So let's say that you're interested in mean differences across your outcomes. I want to know if condition A is different than condition B, then it's different than condition C. The way that I would approach that is to stick all my outcomes in one column, and then whether it belongs to A, B, or C is a predictor. Then I can look at mean differences in a traditional sort of linear model way because I'm thinking of my outcome as one thing, like it's performance. I just have different conditions of it. That same thing would be true if it were longitudinal data, where let's say I'm measuring performance at time 1, time 2, time 3. Like it's conceptually like one outcome in your head, even if you have multiple measures for it for the same sampling unit. You can also do this if you're interested in differences of the slopes of predictors. So let's say that you have an intervention designed to improve student mental health, and you're unclear about whether you should use measure A of depression or measure B of depression because the literature is divided as to which does a better job, so you have them both. Maybe that's one of the questions that you answer. Is the effect of my intervention picked up more if I use measure A than if I use measure B? Or does my intervention have a bigger impact in reducing depression than it does in reducing anxiety? So questions about differences in slopes across outcomes require all of the outcomes to be part of the same analysis, and you can answer those questions with this type of univariate software framework. Can you envision how you would do this, by the way? Differences across slopes. Does that sound familiar? Like what you've been doing all damn semester, right? Linear combinations for slope differences? It's back! This idea of linear combinations of fixed effects shows up in like so many different places. This is why I'm making sure you're really good at it, because if you can do this, you can do anything. So those are two cases that come to mind right off the top of my head. For generalized models, though, this is not a good strategy. So this is a fine strategy for extensions of general models for conditional normal outcomes. But for generalized models, what ends up happening is that because your outcome is stored in one column of data at this point, you only get one version of whatever variance model parameter is required. So let's say that I have a negative binomial stretchy thing, and I need a different stretchy for condition A than for condition B. Too bad. There's no way to do that. Because from the software's perspective, I have a column, and I'll give you a stretchy for that column, whether it's A, B, or C as a predictor. The same thing is true for proportional odds models for ordinal data. The submodel intercepts are constrained equal across the conditions for the same reason, because from the perspective of estimation, it's just one thing. So this is a nice idea when everything is nice and well behaved. It quickly becomes infeasible when you head into the world of generalized outcomes. So for that, we turn the corner and we get into what I call truly multivariate software, where truly means it's not just a hack, like it really is multivariate. And that is known as path analysis or path modeling when you're dealing with observed variables only. If you add in latent variables with which to build measurement models or otherwise introduce additional sources of dependency, then it's called structural equation models. I teach that class too. I don't do path analysis in that class because it's all observed variables that have nothing to do with measurement. I focus on measurement in the measurement model class. That one will probably come back spring 24, I think, give or take. So SEM is every 2 years as well. So in path analysis, the distinction in terms of the estimation is that you can predict multiple columns at the same time. So that allows you to have variables that serve the role of both predictor and outcome simultaneously, such as in a classic example of mediation. So this is a gesture question. Have you seen the mediation triangle thing? You got X at the bottom, M at the top, and then Y's over here. So if that's the way you're thinking of it, mediation is like a causal ordering. I have X, which causes my response M, and M in turn causes my response Y. That's the idea of this. So M here is the issue, because from the perspective of being predicted by X, M is an outcome. M has a distribution that I have to worry about getting the right kind and the right link function and so forth. But then from the perspective of predicting Y, simultaneously, M is a predictor. It's both. So I need a way to be able to separately predict a column of M and a column of Y, and however many other outcomes that I want to have. So path modeling is basically like regression, with just multiple of them at the same time where they can be interconnected. So it's really flexible, and because from the perspective of the estimation, it's separate columns, that means each column can get its own distribution, its own stretchy factor, its own set of submodels, its own everything. So there's a lot more flexibility. However, the choices that you have for link functions and distributions can be more limited. So I tend to use path analysis within M+ software. Stata has a bunch of choices within their GSEM option, and R doesn't have a lot of choices for generalized models unless you're willing to go Bayesian. So if you're like in the STAN or what's the other one? JAGs, I think, R-JAGs, I don't know. The Bayesian ones where you basically can write out your own model and do whatever you want. Speaking of which, at the beginning of the semester, I asked our tech support to make sure that each of you has access to M+ on the U Iowa Virtual Desktop. At your nearest convenience, please log into it and see that you do, because you're going to be using M+ for your last assignment in the class, and I want to allow time for that to be updated if needed. So please check your individual accounts. You have to connect to the VPN, the private network thing first if you're off campus, and then log into Virtual Desktop, go to the software options, and then see what you have. I have, if you don't know how to do that, I can direct you to resources to do that. I have videos in various places on my website of how to do that. So for both of these analyses, one distinction that's important in terms of what happens to missing data. So the traditional version of repeated measures ANOVA, or what is known as MANOVA, is done via least squares. Least squares is the problem with those models. The models are fine, but using least squares estimation means that you can't have any missing cases. So unless they completed condition A, B, and C, they're gone. In the models that we're going to look at within this tricking univariate software and within the path analysis multivariate, we're using likelihood estimation the same as usual. So the assumption that we're making about cases that have incompleteness to them is that anything that's missing is missing at random. That means conditional on all the values that we do have, it's random. But that means we don't have to kick out people who are incomplete. So it helps with your inference, it helps with your power. All right. 3 o'clock. How are we doing? Excited? I think multivariate's exciting. This is like the key to a whole new world. Questions? Yeah, hit me.
When you tell the multivariance model that's used, like it's true multivariate, can they use to predict the generalized model then?
You can, but with certain limitations. So for instance, within M+ software, which is probably like the one that I tend to default to for path models or SEM, they have binary, ordinal, nominal. They have counts, they have zero inflated counts. They don't have gamma. They don't have anything like quantile. They don't have anything binomial. But they do have censored, which is Tobit, and they have two-part. So like the binomial one is the one that's hard to find. I want to say that that's in Stata's GSEM package. G stands for generalized. In R, for instance, you can do path models in Lavon, but you can only do ordinal or binary. There's no other choices for that.
That's why, because my data with homework 5 is actually repeated measure, it's the outcome is proportion, like it's percentage correct. So that's why I can't use that because M+ doesn't have the.
Yeah, the only one I think you could use is Stata, but we won't have covered, like by the time you need to do that, we won't have covered those models very well, which is why I probably told you to put them in separate analyses for now. Yeah. Because yeah, I'm expecting that like your individual data analyses cover things that we've already done, not things that we're currently working on, because I don't feel like that's fair to ask you to learn it and then turn around and do it 10 seconds later, you know. But yes, once you figure out how to do it once, putting it into the same analysis is not that much more difficult, but it does change how you would do it in terms of the estimation. Other questions or comments? All right. So then, starting with general linear models to begin with, and then we'll have examples with generalized because we're just getting sort of the multivariate part set right now. There's two strategies by which you can incorporate relationships among the residuals that come from the same sampling unit. Directly or indirectly. Directly is literally you just tell the software, let the occasions from the same person be correlated, thanks. And that's it. In terms of path models, this would look like specifying a relationship between two boxes that is a curved arrow. So there's probably a term for this in terms of like the DAG? Directed acyclic, whatever. Is there a name for a two-headed arrow in those? No? I know there's like edges and nodes and like all kinds of stuff, but two-headed arrow is the key idea here. So it looks different based on what you're doing in software, but conceptually it's just let the occasions from the same person be correlated at the end. Super easy. So in this case, the linear predictor, or the fixed effects in the model for the means, will only have fixed effects because all of the relationship is captured just directly by the correlations between the residuals. Great when you can do it. However, the only situation in which you have a separately estimated residual variance is if you're using a conditional normal distribution. There's nothing else we've seen this semester that's worked the same way. You might have an extra stretchy over dispersion factor for like your beta binomial or your negative binomial. For gamma, you might have something that looks kind of like that, but there's no separately estimated residual variance. Well, if you don't have residual variance, you can't have covariance either. So this strategy of just let the residuals be correlated is only for normal models. For something else, we have to do it indirectly by adding what is known as a random intercept, or random effects more broadly construed. So this is a more general strategy that works for generalized models. It also works for unbalanced sampling designs beyond just balanced. This is something I'm going to spend like 5 seconds waving my hand at pretty much this semester, because I cover it in way more detail in the other classes in which it's more relevant. But I want you to be at least exposed to it to start with. So to understand the difference between these, we have to do a little bit new vocabulary and a little bit of matrices. Not a lot, because I don't like matrices, but just a little bit to try and describe sort of what's happening under the hood here. So let's say that we have this general linear model here. I call this scalar notation because this is written like, you can picture sort of a column here and a column here, but it's written so that you can directly see what's included. First off is the direct way of incorporating correlated residuals. So let's say that we have 6 people and each person only has one outcome. So just starting with our usual independent observations to start with. So if I were to write out this same formula in the way that we're used to seeing it in matrices instead, it would look like this, where y is an outcome vector that is n long and only 1 wide, so 1 column, bunch of rows. We have x beta, which Ariel would call X the design matrix, if you've been through design of experiments. That's the matrix that holds the predictors that have fixed effects. Beta is the matrix that holds the fixed effects themselves, and then E is my residuals. So like if I wrote it out for all 6 people, it would look like this, where this column right here is for the fixed intercept, because beta 0 doesn't multiply anything. In order to have it show up in this notation, it's like I have to put an implicit 1 behind it here so that we have enough spots for everything to work out. And in this E, what's not obvious here, that we're assuming that these are unrelated. Like there's nothing in this equation that tells me that directly, other than the words that go with it. But this is really what it looks like sort of under the hood from an estimation standpoint. We're saying that everybody has the same residual variance, and the zeros here imply no covariances. So like this is the 6 by 6 full set of data for my sample. Everybody has the same residual variance on the diagonal and then no covariances. So what we have to do to allow residuals to be correlated in particular patterns is change these zeros into different things. This is called an independence structure because of the zeros. It's also called diagonal sometimes. In SAS, it's called type equals VC, which stands for variance components. Question?
Yeah, is this sort of like when you're like trying to like run a test to like assess for like sphericity, like in a repeated measure?
Yes. So it's adjacent to that. So like this would be, so if you're talking from an ANOVA perspective, like the word sphericity is referring to an assumption that you make in repeated measures ANOVA. Like this would be a between groups analysis where there's no relationship whatsoever. In a within analysis, we need there to be a relationship instead of zeros. The question is what kind. So one option is what's known as, this is a couple slides from now, compound symmetry, where all of these zeros are the same number and all of these are the same on the diagonal. In order for the standard univariate repeated measures to hold, what actually has to hold for this pattern is sphericity, which means that the pairwise differences have equal variance and covariance. So this is like the jumping off point from those further choices. So it is related, but we're not to that point yet. Sphericity, by the way, is only a thing in least squares land. Because once you enter the world of likelihood estimation, you get all kinds of other choices. You don't have to have it be spheric. Is that the word? Spherical? Spheraceous? I don't know. I don't know what sphericity turns into.
It doesn't like resemble, I mean, I don't know like if it actually resembles like that.
It's not a circle. Like I don't
Right.
think spherical works for this, but sphericity is just, yeah, what that means is that if sphericity doesn't hold, then you go to the other choice, because in least squares ANOVA land, there's only 2 choices. Everything's the same or everything's not the same. Whereas there's about 37 more choices once you move into likelihood land, because you can do whatever you want. All right, so this is like this is what we're actually assuming sort of under the hood about the E's here. They're independent across people with constant variance. So how do we get from that to where we need to be? Is we're changing our definition of height. So do you remember this picture back at the beginning of the semester? This is our univariate normal distribution that I stole from Wikipedia, of course. This is the formula for it. So if I know what the predicted value is for each person and I know what the residual variance is, I feed those numbers into this formula, and for each person I get one number back out that is the height of their y under the current model parameters. And the process of figuring out what the answer should be is the process of figuring out the model parameters that collectively make everybody's data the tallest. So we looked at a function like this as an example, where I have these 10 observations, I think there's 10 or so. I know based on just computing the answers here what the mean and variance is, and I have the height of each person as the green line here under the right answers. If I plug in alternative answers, so the mean is just a little higher, but the variance is way lower, then collectively the data are not as tall. For the people in the middle here, it's actually a little taller, but for most of the sample, it's much less tall. So likelihood estimation is the process of trying out different values of these model parameters to figure out which ones collectively make everybody the tallest. But the key to figuring out the sum of the heights is independence here. So we take the log of the height and we can add them together. If it were just the regular likelihood, then we'd have to multiply them, and then we have numeric instability problems. But the idea of just adding these is predicated on independent observations. So what if, like, the first, second, and third come from the same person? Well, then we shouldn't just add them together like they're 3 different people. We need to find a way to, like, okay, what is the height of, like, this set of observations at the same time? Like, your 3 outcomes, what's your height? Your 3 outcomes, what's your height? Your 3 outcomes, what's your height? I feel like Oprah. You get a car, you get a height. To do that, we got to restructure the data, and we got to make multivariate normal instead of univariate normal. So that's where we're headed. But it's 3:10, so we're not headed there today. Multivariate normal looks like a taco to me, like a taco shell. So then we have height in multiple dimensions, where if there's no relationship, then it looks like a big, like, circle mountain thing, and if there's a relationship, then it looks like a taco in one direction or the other. So that's the answer, is maximizing the height of a set instead of just one. And we have the same choices for how height is determined in terms of based on a distribution. So, all right. Any questions before we call it a day? Not a week yet, it's only Tuesday. Although it sort of feels like it should be Thursday by now, but it's not. No questions from the roomers? How about the Zoomers? Hanging in there? I think the Zoomers have lost their will to live. It happens, I understand, it's that point in the semester. There's a few thumbs. Yes, I feel like I'm running on a treadmill, and someone just keeps, like, cranking up the incline. I'm like, but I'm still going fast. Why is this so much harder? Because eventually your legs get tired, and then we have summer break. But not yet. All right, then I have office hours tomorrow if anybody wants to do last-minute homework questions, because it's due tomorrow night. Otherwise, we'll pick up this on Thursday, and I shall see you then. Thanks for being here.